Hello and welcome to this video presentation of our DART project. The goal of this project was to estimate CO2 assimilation by the forest canopy using remote sensing. To do so, we used the DART radiative transfer model to simulate radiative transfer over a forest canopy. Forest canopies are one of the main sources of CO2 absorption on the planet. Leaves use the solar energy for the photosynthesis, which converts CO2 into organic matter. The quantity of CO2 consumed during the process can be obtained through the gross primary production, or GPP. During this project, we estimated the value of GPP in 3 different cases. The first one was a dense forest with no atmosphere. The second one was the same forest with the atmosphere simulated. The last one was with a sparser forest, also with the atmosphere. But first, we must define some parameters that will be crucial in estimating the GPP.
The photosynthetically active radiation domain, or PAR domain, is the spectral domain between 400 and 700 nanometers. It is the bandwidth that is used by vegetation for the photosynthesis. The incoming solar energy flux restricted to the PAR domain can be calculated by taking the integral of the solar irradiance on the PAR domain. The fraction of absorbed photosynthetically active radiation, or FPAR, is defined as the fraction of the solar energy flux in the PAR domain that is absorbed by the canopy. The expression for it is the following. Since in DART every pixel of the image corresponds to one value of reflectance, we calculate the mean FPAR. The NDVI in the formula is here to discriminate between pixels that are vegetation and pixels that are not.
The first simulation we ran was without the atmosphere. In this configuration, the flux received by the canopy in the PAR domain is the incoming solar flux in the PAR domain. The canopy reflects a part of this energy back up and absorbs the rest. The absorbed energy can therefore be expressed as 1 minus the reflectance of the canopy in the PAR domain times the incoming solar flux. Here are the DART parameters we used for this simulation.
First, we defined 3 spectral bands, one ranging from 400 to 700 nanometers, which is our PAR domain that we will use to calculate the FPAR and the GPP. The other 2, one at 670 nanometers in the red domain and one at 800 nanometers in the infrared domain, those 2 bands will allow us to calculate the NDVI. These are the parameters that we chose felt like a good compromise between precision and simulation runtime. We made sure that the sun was aligned with the nadir view of the sensor to avoid any under-evaluation of the reflectance due to shadows. We defined 5 Lambertian surfaces used to simulate the properties of the trunk, the leaves, the branches, and the bark of the tree, as well as the soil. We decided on simulating a forest of beech, so we defined the leaves as deciduous leaves, and the bark and the branches as beech. For the trunk, we didn't find a database for beech trunk, but we made the assumption that the optical properties of the trunk were not too important for estimating CO2 absorption, and we chose the optical properties of a Citrus sinensis trunk.
We set the temperature parameters between 290 Kelvin and 310 Kelvin, or 17 degrees Celsius and 37 degrees Celsius, placing the scene in a warm summer setting. The scene was set as a 50 meters by 50 meters square. We used a Python script to generate an array of randomly yet homogeneously placed trees using Poisson's disk sampling. This method had the benefit to generate very realistic forest canopy. As for the geometry properties of the trees themselves, we made sure the trees were not the same by allowing a standard deviation in size of 5% for each axis, as well as deviation in rotation of 180 degrees.
After running the simulation, we obtained images of the scene for each of the spectral bands. Using a Python script that converts the brightness of a pixel to the value of reflectance, we calculate the f-bar of our forest canopy for this simulation. To calculate the GPP, we simply multiply the incoming solar flux with the f-bar and with the light use efficiency coefficient. This coefficient depends on the type of leaves. Values of light use efficiency were found in the literature. For deciduous broadleaves, the coefficient is equal to 1.434 grams of carbon per megajoule. We obtained a value of f-bar of 29.2%. We obtained for the simulation 9.59 grams of carbon per meter squared per day. This value is bigger than what could be expected from a beech forest. This difference may be due to the lack of an atmosphere in the simulation.
We ran a second simulation with the atmosphere simulated this time. In this configuration, the part of the incoming solar radiation that is absorbed must be multiplied by the transmittance of the atmosphere. The transmittance depends on the wavelength, so the incoming radiation integrated on the wavelength is the following. Dart parameters were not changed for this simulation, we only added the simulation of the atmosphere. We set the optical properties to be that of a mid-latitude summer atmosphere, and CO2 mixing rate value is taken from the Mauna Loa data for June 2024. We set the aerosols properties to be those of a mid-latitude summer rural zone, since we are studying a forest. With this simulation, we found the value of f-bar equal to 13.2% and a GPP value of 8.16 grams per meter squared per day. Although lower than the previous value, it is still above the 3.14 grams per meter squared per day that is expected for our forest. This may be because our forest is very dense, with some places where the trees overlap each other.
That is why we ran a third simulation with the sparser forest. The dart parameters didn't change, only the tree placement. On the left is our previous tree disposition, and on the right is the new one. With this last configuration, we found a value of f-bar of 8.1% and a GPP value of 5.10 grams per square meters per day. By changing the density of our forest, we are getting closer to the value we should have. In conclusion, we saw that using the reflectance in the power domain as well as the NDVI, we can estimate the CO2 assimilation of a forest canopy by using remote sensing. The value of GPP we calculated was above what should have been found, but this can be explained because some parameters were neglected for simplicity or lack of proper tools, such as the atmosphere reflectance, optical depth, or the leaf area index.